talk about the chemical formulas of ionic compounds. Okay? All right, so this first picture, I don't even know. Oh, yeah, it's right there. It's very small, but it says that this is a pure covalent bond. Okay? So this is our representation of a covalent bond, and then we're going to look at one down here for ionics. Okay? So in this particular representation, this is a hydrogen, 2 different hydrogen atoms. I know that because there's only a single electron shown, so. And we're looking at what causes the hydrogen atoms to come together and be H2, or 2 hydrogens bonded together. Now, on the next page, you'll see a bunch of elements in yellow that are called diatomic molecules, or sometimes diatomic elements. So the ones in yellow, don't worry about the pink ones, but the ones in yellow, you're going to have those memorized. I mean, don't like memorize them as a list. Just visually memorize them on the periodic table. So hydrogen is weird because hydrogen is a non-metal, but it's on this side of the periodic table because of how its electrons are structured, okay? Its electrons are structured more similarly to these guys than it is to these guys, but it kind of sort of belongs on this side as far as metal versus non-metal, okay? So hydrogen out on its own over there, and then if you look at nitrogen, oh, that's fascinating. I've never noticed that. There's 7 diatomic elements, and I always say they make a 7 on the periodic table in this corner. But look, it starts at element 7 too. Ooh, spooky. So that's helpful because I guess you could mess it up and like think it's these 7 if you didn't know that. But it's the halogens, and then nitrogen and oxygen and hydrogen over there. So those 7 elements will never appear by themselves like just a single nitrogen or a single hydrogen. They will always come as pairs. So it will be N2 or H2 or O2. Now, they can obviously be individual in a compound. So, like, I can have CO, which is carbon monoxide, and that's an oxygen. It's not by itself, though. It's in a compound with carbon, okay? It's that you will never see an oxygen, a single oxygen by itself. It'll always come as a pair. You could see a single carbon by itself. That's totally normal because it's not one of those diatomics. Or like magnesium or something, or silicon. Like all of these could appear by themselves. These 7, though, will always appear as a pair if they're not in a compound with something else. They will be in a compound with themselves. They'll make a molecule themselves. So when I say oxygen gas reacts with CH4, you need to know that when I say oxygen gas, I mean O2. I don't mean O. Whereas if I said magnesium reacts with something, then that can just be Mg by itself, okay? But if it's one of those 7, you need to know that when I say it, it's a pair. So like the nitrogen that's in the atmosphere, the oxygen that's in the atmosphere, those are N2 and O2. Okay, so what we're talking about here is H2 and how that bond forms. So we've already talked about the fact that you have an attractive force between the electron and the nucleus, right? This is what ties them together, and this is what is related to energy. We talked about the attractive forces between positive and negative being related to energy, and that's like a good thing energy-wise. It lowers potential energy when positives and negatives can be attracted to each other, okay? So you've got these 2 atoms, they have their own electrons, and they're attracted to the nuclei. When you bring the 2 atoms close to each other, this electron on this atom starts to feel the attraction to this nuclei on the other atom, okay? So because that is a good thing, it lowers potential energy even more. You can think about it like when we made this analogy to gravity, we said that it's like if you have the 2 charges separate, then when they get attracted to each other, they come down the hill, like, or I drop the pencil, like that's lower potential energy, is things that are attracted, the pencil and the earth, will want to come close together, and that is a lower potential energy situation. So like the positive and negative being completely separate would be here, and then when they form an atom like this, that's down the hill. When you form another attractive force, that makes you come down the hill even more, okay? So having these two things attracted to each other and having these two things attracted to each other starts to lower that potential energy even more and forms like a favorable thing. It's why the pen will drop or the ball will go further down the hill. If there's somewhere lower in potential energy it can go, it always will, okay? So these two atoms start to be attracted to each other and pull closer and closer because those electrons are like, oh sweet, now I can be attracted to two different nuclei instead of just one. So they come together and that forms a chemical bond. Okay, so when we say a chemical bond, specifically a covalent bond, don't worry about this pure word right here. We'll come back to that later. Specifically, a covalent bond is when the electrons are now able to be attracted to two nuclei, and we call this electron sharing. Again, sharing because that electron is being attracted to two nuclei. It's being shared between the two. Okay, so we would represent that with the chemical formula H2, meaning there's two hydrogens, they're bonded chemically together. Okay, so on the 2 slides down, so we already talked about the diatomics, so we're skipping over that. A, this picture A, the rest of them aren't labeled, so I can't say it as A. This one here is another example. This one happens to be chlorine. So it's showing this chlorine's electrons are all in yellow, and then this ones are all in orange, and it's showing that these two, like one from each of them, gets to be attracted to both nuclei. Okay, so again, they're sharing those electrons. A key point about these covalent bonds is that they are nonmetals, okay? Covalent bonds are always going to happen between nonmetals. Let's go back to the periodic table, just as a good reminder. So nonmetals are these guys on this side of the stair step. So if we're talking about any of those bonding, oh, and hydrogen. If we're talking about any of those bonding, it's going to bond just like we talked about, this electron sharing idea called covalent bonding. It doesn't look like very many, but there's lots of things you can do with all of those elements. Something like that's unique, and you'll see why in a few minutes, is that you can have lots of variations between like two given elements. So carbon and hydrogen are both nonmetals, and you can see carbon bonding with 4 hydrogens. That's basically natural gas. This is methane. So when we talk about gas, not like gasoline, but gas in the terms of what they pump out of the ground, most of it is CH4. There's also some ethane in there, which is C2H6. You don't have to know the specifics. I'm just using this as an example. And sometimes you get some weird variations of the C2 compounds that are like C2H2 or C2H4. So what I want you to notice is there's lots of different combinations of carbon and hydrogen that all have really different properties. And it's totally fine in covalent compounds to have all these different variations. Another like maybe simpler example is carbon monoxide is 1 carbon and 1 oxygen, and like that's poisonous. Carbon dioxide is 1 carbon and 2 oxygens. I guess since we expel it, you could think of it as also being poisonous if you had too much of it and not any oxygen, but much less so than carbon monoxide. So carbon and oxygen, but 2 different ways that they bond and form 2 distinct compounds. That is different than ionic bonds. The reason I'm emphasizing this right now is it's very different than ionic bonds. So ionic bonds are formed between a metal, so a pink one, and a nonmetal. So this is a question I get at the end of chapter 3 or 4, or they're like getting ready for the test and they're like, I don't understand how to name them though, because how do I know if it's an ionic or a covalent? A covalent is always just nonmetals. An ionic is a metal with a nonmetal. So that's written down right here. Highlight it for yourself if you need to. Covalent is nonmetals. This one over here, we're going to come back to, don't worry about this polar or nonpolar thing. We'll come back to that. But the star is for me, so I know we need to come back to it. They're both nonmetals. They're both variations on covalent bonds. Whereas an ionic bond is a metal with a nonmetal. Okay, so let's hone in now on ionic and talk about what that is and how it's different. Okay, so when we talk about ionic, it is definitely not sharing electrons. It is what we call electron transfer. So it says complete transfer here. I'm just going to rewrite it here. Electron transfer versus electron sharing. So you can think of covalent bonding as like the 2 atoms are playing nice with each other, okay? They're both playing with the toy or whatever, the truck, and they're taking turns and they're sharing it, right? Ionic bonding is a bully situation. The chlorine, the non-metal, it's always the non-metal, it's the chlorine in this instance, but it's always the non-metal that's the bully. It actually takes the electron from the metal. So the electron gets transferred from the metal to the nonmetal. And then what happens? Why does that create a bond? Because the metal is now positively charged. Just like we knew this happened, we actually talked about this last unit. Oh, I don't have that picture right away. Stop. It made my picture go away. Let me try again. There we go. Okay. We talked about this last class. Let me just pull it up. Don't worry about where this is. It's down here. So we talked about this in the last unit, that the metals tend to lose electrons, and we know based on their column how many they're going to lose, but we know they lose them in ionic compounds. Nonmetals gain them, number based on what column they're in, but they gain electrons, and this is when this happens. The nonmetals are the bullies. They take the electrons away from the metals, so now you've got a positively charged ion and a negatively charged ion. And it's the same type of attraction now, positive and negative, but instead of an electron being attracted to a nuclei, that's also a positive negative attraction that happens in covalent bonds. In ionic, it's a positive ion now. It's a whole atom that is positive and a whole atom that is negative, and now those are attracted to each other. You can kind of think of it as like the non-metal. I'm going to pull this analogy that just came up with this whole bully analogy. It's not one I've used before. So let's see how far I can extend it. So the chlorine's the bully, and it takes the toy away from the metal. But now the metal like will not leave the bully alone because the bully has their toy. And so they just like constantly are following them around, wanting their toy back. okay? So the positive and negative ions stick together, not because they're sharing something, but because they're oppositely charged. One has the toy and one doesn't have the toy. Okay, now we have a very different structure of the compounds that happens because of how different their bonding is. So, ionic bonds, I don't want to zoom in too much. Just focus in on the left-hand side right now. Ionic bonds, which are made of ions, that's why they're called this, positive and negative ions. We're going to use the example of NaCl here, so Na plus and Cl minus that are now stuck together. When we write their formula, we do not show the positives and negatives, so it's just written as NaCl. And because the electrons get transferred and create these ions, there is a very set formula that every combination of metal and nonmetal will have. So by that, I mean NaCl is always NaCl. It's never Na2Cl or NaCl2 or anything like that. Remember, I just showed you these examples of carbon and hydrogen and oxygen that can have all of these different combinations, CO, CO2, HCO, like all these different variations of how carbon and oxygen could bond. NaCl only has one way that it will bond. It's always going to form one Na for every one Cl. This is because because they're charged, they will only pair up in a way that creates a neutral compound. So if I have a positive 1 charge and a negative 1 charge, we just want one of each to pair up together. Let me give you a different example. If I had calcium instead, so if you remember, I'm going to have to scroll down. Calcium is in the second column here. It's that guy. So it's going to form a 2+ ion. So instead of sodium, let's pretend we have calcium and see how that would be different. So calcium is a 2+ ion, and chlorine is a -1. So chlorine took away 1 electron from calcium, but that's all chlorine wanted. So another chlorine had to come along and took away the other electron from calcium. So the formula for calcium and chlorine together is going to be CaCl2, because they always are going to have to balance each other out. So if we know that calcium forms a 2+ ion, if it combines with chlorine, which we know forms a -1, there's got to be 2 chlorines for every 1 calcium. They always have to balance out to 0. So think of it as just adding them up. +1 and -1, that's 0. +2, oh, I must need 2 -1s to balance that out. And the formula for calcium chloride will always be CaCl2. It'll never be CaCl or CaCl3. Unlike covalent bonds, which can change those, numbers of atoms really easily, when we're talking about ionic compounds, they have to balance each other so that the overall charge is 0. We'll do some harder examples in a second. Okay, what do we mean by CaCl2 or NaCl in the example of an ionic compound? We do not mean that there is a single sodium and a single chlorine that stick together. There's actually a big mass of sodiums, sodium plus and Cl minus, that all are kind of intertwined together. They're still in a ratio of 1:1. Like for every sodium in this picture, there's also 1 chlorine. So if I had like 1,000 sodiums, I would also have 1,000 chlorines. That's a 1-to-1 ratio. If it was calcium chloride, if I had 1,000 calciums, I would need 2,000 chlorines, right? This one's a 1-to-2 ratio. So the formula doesn't tell us exactly how many of each one we have. It only tells us a ratio. And this is just inherent in how ionic compounds form. When they do these ions, they don't clump off in little individual NaCl's. They just make this big crystal that has a ratio of 1 NaCl to 1 chlorine. Yep.
So is this what like they want to do? Like they want to not have charges?
Yes, because anything that has a charge will end up reacting with something until it's neutralized.
Okay.
So think of like static electricity. That's trying to discharge something. Like I just realized I said it's trying to discharge, and I was like, it's discharging charge. It's like you have built up negative charge, and it's looking for a source to neutralize it. So if you had 1 calcium 2+ and 1 chlorine minus, it would be looking around for something else to balance it out. Yeah. So this is ionic compounds look crystalline for this reason. So like if you think of like salt crystals that come out of a salt shaker, those are really fine. They still have lots of sodiums and lots of chlorines, but they're still in a 1-to-1 ratio. If you get a bigger, like if you use like kosher cooking salt, it has like bigger granules and you can see those crystals. Or if you get as big as like a salt lick for horses, my sister has horses, so it's the only reason I know this, but it's like a block of a salt crystal. It's huge. It looks like ice, but it's salt. So it still has that same sodium to chlorine ratio. You can't really break it down anymore chemically. You just physically would break it down into smaller chunks of crystals. Okay? Covalent bonds are totally different in how they form their actual structure. So this picture is glucose, and it has the chemical formula C6H12O6. So that is the actual number of atoms, 6 carbons, 12 hydrogens, 6 oxygens, that will form one individual little glucose molecule. And this is probably more what you guys are familiar with, because I think other than some engineers in here, I think the vast majority of you guys are in some kind of biology program. So this is what you're probably more familiar with, is seeing individual molecules. And also because, like, you know, we are biological systems. And so a lot of the times when we talk about stuff, we're talking about things we're interacting with. Okay? So covalent compounds form little units, not one big mass of stuff, but individual little units that we call molecules. So it's not actually appropriate to use the word molecule for ionic compounds because there isn't a distinct little unit of NaCl. So that, you'll hear the book call it formula units sometimes. They mean like how many NAs do you have for how many Cls, but there is no one NaCl molecule. That would be a wrong use of the term molecule. In covalent compounds, we see these little units all the time. So think of like a water molecule, right? It's got a hydrogen with an oxygen, so they're sharing electrons, and then there's another hydrogen also sharing electrons with that oxygen. And those little water molecules can be floating around by themselves, behaving independently. So like if they're in the gas phase, there'd be a little water molecule here, a little water molecule there, all over. If you start to cool them down, they'll interact with each other and form a liquid, but they're still their own little distinct water molecules. Even if you look at ice, you can still identify each little individual water molecule separate from the other one. There are just interactions that hold them in the shape of ice. Okay? So glucose, same thing in this picture. Each one of the little black ones represents a carbon, the red ones are oxygen, and the white ones are hydrogen. And if you counted that up, there's going to be 6 carbons, 6 oxygens, and 12 hydrogens. So when we write the chemical formula of a covalent compound, it does not just indicate a ratio. it indicates the actual number of atoms that exist in that molecule. So it would not be appropriate to talk about this in the form of CH2O. If we wanted to fully describe the molecule, that's no good, okay? We do use this term sometimes. It's called an empirical formula. I'll like highlight it specifically in a slide or two. But it doesn't tell us about the real nature of the molecule. So we don't really want to reduce it down to a particular ratio because we lose a lot of good information, because the actual molecule has 6 carbons, 12 hydrogens, 6 oxygens. You could have another molecule that has that same ratio, like 3 carbons, 6 hydrogens, and 3 oxygens, and it would have completely different properties than the glucose molecule does. Okay, so the chemical formula in a covalent compound means how many atoms are in that actual molecule, whereas the chemical formula in an ionic compound is simply just a ratio of the ions. No, just on that one. Okay. Yeah, it's a little hard to tell handwriting on bubbles. Thanks. Okay, so when we look at covalent compounds, we always do want to reduce them down to the smallest whole number ratio. So we would never do that with covalent compounds. With ionic compounds, we always want to reduce it down. So that's right here. Formulas are always reduced to the lowest whole number ratio. So let me show you an example of this. If we had magnesium, which has a 2+ charge because it's in the second column, and we had oxygen, which has a 2- because it's in the, 6th column, those would still be one of each. We would not write this as like Mg2O2 because that's still a 1-to-1 ratio. In fact, I think you guys probably wouldn't even think to write it this way. Just if you ever come across something like this, it's not right. You always want to reduce it down to the lowest whole number ratio. If I have a 2+ magnesium ion, I just need a 2- oxygen ion to balance them out. They just need to be one of each. Okay, so the correct formula for magnesium and oxygen would just be MgO. So ionic compounds, let's just do a summary real quick. Ionic compounds, metal and nonmetal, their formulas are dictated by the charges needing to neutralize each other. So they have to be equal to 0. And because of that, there's always a set ratio for any pair of metal and nonmetal. Calcium and chlorine's always going to be a 1-to-2 ratio. Sodium and chlorine's always going to be a 1-to-1 ratio. Okay? And then their structure is just a ratio of ions. It's not individual little units. Covalent compounds can form whatever combination they want to of atoms. The formula tells you the actual number of atoms in that little unit, and they will have these little units. They won't be just a big mass of carbons and hydrogens and oxygens. They'll be these little distinct units, molecules. Those are always all nonmetals. Okay, any clarifications on that before we finish up by predicting charges on ionic compounds? Because we'll kind of focus a lot on ionic compounds for Wednesday and then just kind of come back to covalent. Okay, I want to do one, I feel like I'm squeezing things in here. Let me do this as just kind of a break for a second. Predict the type of bond between these elements. And then I'm going to use, then we'll do one example before we do another practice. Okay, so ionic or covalent, that's all you're looking for on these ones. Okay, so you need to remember the definition of ionics or metal and nonmetal. Covalent is all nonmetals. In this instance, you need to make sure you know the symbols, or at least know if it's a metal or nonmetal. I would say know the symbols, and then you can find it on the periodic table. So the only one there that's ionic is the lead and oxygen, because lead's a metal. Okay? All right, lead is a little bit weird. I don't want to explain why right now. But I'm going to tell you, let's just pretend that lead is a 4+ ion. What's the charge on the oxygen? 2-. I feel like I heard a whisper there. 2-, okay? It's based on the column in the periodic table. This one I told you, okay? This one's from the column on the periodic table. Okay, if lead and oxygen want to form a compound, what would the formula have to be? It needs to equal 0. So we're going to have 2 oxygens for every 1 lead, because we're going to have a 4+ on that side. That means I need to have 4- charges on the other side. So the formula would be PbO2. Again, you're just pairing up the ions so that overall there's a 0 charge. Okay, so to practice this is going to be probably our last thing. You can refer back to this table if you need to, but I want you guys to practice predicting the formulas of these compounds. These ones, you will know the charge based on where it's at in the periodic table, and these ones I'm giving it to you because iron's one of those that can change. Okay, so try to predict the formula based on charges if you had an ionic compound form between these two things. Maybe I'll write a couple steps, like how-to steps if you're lost. Okay, so you're first going to determine the charge, which you know from the periodic table based on their location, or it's given to you in the case of the iron. So I wrote those down in red. Then you want to use enough of each ion so that they balance out and give you an overall charge of 0. So like for the first one, sodium and oxygen, I need 2 sodiums to balance out that oxygen's negative charge. So the formula would be Na2O. Okay, so I'll just give you another minute to finish them up, and then I'll write the answers up here and you can check. So let me let everyone finish checking their answers, and then I just want to show you guys kind of like a trick to figuring this out. So some of them are pretty obvious, like Ba2 plus and S2 minus. Okay, great. They balance out, so I just need one of each. Terrific. Lithium and phosphorus. That should kind of make sense. Phosphorus is 3 minus. Okay, I need 3 of those positive ones then to balance it out. So that's like the compound, we're simplifying it by writing Li3. It's like 3 lithiums for every 1 phosphorus. Okay? Well, when you get to Fe3 plus and O2 minus, that starts to feel a little bit like, what? How many do I need of each of these? If you notice, this is like a least common multiple, I think is the right term. So whatever number is up here, that's how many you're going to need of this. And whatever number is up here, that's how many you're going to need of this. Because if you have 2 of these, that's a positive 6. And if you have 3 of these, that's a negative 6, and now they balance. Okay? So you can see, like, this number comes down there, and that number is down there. You want to, like, verify it for yourself a couple times. Yeah, if you just swap them, that totally works. You just have to make sure that you reduce it. Because if you swap these, you would get Ba2S2. And you want to make sure that you reduce that to BAS. Okay? All right, we'll pick up there on Monday.
It's the only thing I understood about chemistry.
It doesn't have to be your favorite, but you can still do it. Yeah. Yeah. Do you have class at noon on Wednesday?
I don't.
Okay, let's do it then. I'll just put you on my calendar.
Oh wait, actually,
You're like, I do.
Oh yeah, I do. I don't have it at 11. I don't have it right at.
Oh, okay.
That's what. That's what. Yeah.
Yeah.
That's what.
Do you want to do? We could do Tuesday during the day sometime, like on Google Meet, or do you have anything at 1 on Wednesday?
I don't.
Okay, I could probably do 1 o'clock, or I could do Tuesday.
One probably. Is it one be in person?
Yeah.
I'd rather just like.
Yeah, that's fine then. All right, remind me your name.
Reese
Okay, last name though.
Solomon.
Solomon?
Mhm.
Okay. So it'll be in 305, Hale 305, that's just across the hall over there. And, so 1 o'clock, right? Yeah.
One. Yeah, that's what I'll say.
Good, all right,
Thank
sounds
you.
good, yep. Hi.
I was just wondering if we could meet after class Wednesday.
Yes, not after this class, because I teach a class after this.
Alright.
Do you have a class on Wednesday, or sorry, at noon?
I do.
Okay,
I have a freshman seminar.
that's fine. So she just scheduled one at 1. Do you want to say like, I don't know, 1:15 or something?
I have a class at
Do you have a class then too? Okay.
I'm done at 2. I have a break from 2 to 3.
Yeah, I can't do it that late. But we could do Tuesday like on Google Meet if you
Alright.
want. Does that sound okay?
What time?
What's your schedule like?
Tuesdays. I just have a 2 to 4:30.
Okay, let's do it in the morning then. Maybe just like a 10.
At 10.
That sound good?
Yeah.
Mhm. Name?
Ella Detweiler.
Okay. And then I will send you a link. It might literally be when I sit down at 10 o'clock. I'll just
Alright.
email it to you. But yeah, that should
All right.
work.
Thank you.
Yep. Hi.
I can ask this one.
Okay, so do you have a class at noon on Wednesday?
Yeah.
Why does everybody have a class on noon at Wednesday, or on Wednesday? What about at 1, like 1:15 on Wednesday?
No, I don't.
Okay, let's do that. So Wednesday, the 24th, 1:15, not AM. And I was gonna try to guess your name, but I don't think I'm gonna get it right. so go ahead and tell me. Okay. Nothing. Maya, okay. Okay, and then last name? Okay, cool. So yeah, it'll be in 305. Okay, good, I'll see you then. Hello. No, I forgot to send it around. Don't worry about it. All good, yep.